Hi everyone, this is Group 1 and this is our presentation. The group members are,
Jordan Richardson.
Hi, I'm Kylie Moore.
I'm Luis Martinez,
And Mrs. Karan Dhar.
and this is our presentation. So for introduction, we began this project with the goal of using our microprocessor and microcontroller to roll a dice and receive the output. The idea was to use a microprocessor with an IMU. An IMU is an internal measurement unit and typically consists of a gyroscope as well. This would allow us to roll the dice, and if the microprocessor was contained stably inside, receive the output it landed on. We also wanted the microprocessor to be small so that we could create a relatively realistic dice. And we would need a battery as well so it could actually be rolled. We decided on the Seed Shell BLE Sense.
The Seed Zhao was the perfect candidate for our dice. At 21 by 17.5 millimeters or 13/16 by 11/16 inches, we could theoretically make a dice only 2 millimeters larger than a real dice, if we were able to find a battery around the same size. Considering the goal of our project began with soldering a battery and designing a 3D printable dice. After getting our battery soldered to the microprocessor, we began designing our 3D printed dice. Due to a lack of experience in 3D printing, our first model was much bigger than expected. Due to the size of our dice and the small size of our board and battery, we actually had to use stuffing to keep the board in place for rolling purposes. We decided to put off designing a smaller dice for the meantime and began to focus on establishing connection with our microcontroller, the ESP32. This would be done utilizing Bluetooth, which the Seed is capable of, while utilizing low energy. BLE stands for Bluetooth Low Energy.
We were quickly able to get our IMU processing accelerometer data and returning dice side depending on position or rotation of the microprocessor. We began by trying to establish a connection with the ESP32 being the server while the seed was the client. This allowed us to concatenate and transmit the accelerometer data to the ESP32 and allow it to do the heavy lifting such as calculating the dice side. This also later allowed for much easier manipulation of how dice side is calculated.
Using the professor's suggestion, we used InfluxDB to store and receive our data. This was a process as while some teammates had experience transferring data via HTTP, others did not, but we all wanted to learn. So we decided to do our project in two different steps. First, we had our data transmit over Wi-Fi to InfluxDB from the ESP32, and then from InfluxDB to Python by creating a read script that connects to the same bucket. We then alter the script, so instead of printing the data it receives, it writes it to a CSV for storage so that we can access it at any time, as well as perform a wider range of statistics and analysis than InfluxDB allows us to do. This can be a lot to grasp. So just to reiterate over our basic architecture, our seed microprocessor collects accelerometer data, concatenates the three axes of data, and transmits it via Bluetooth to the ESP32. The ESP32 determines the dice side as it receives the data and transmits this value to our bucket in InfluxDB. The Python script then reads from this bucket without allowing duplicates and writes it to a CSV with the time. We then have a script that reads this CSV for plotting and analysis.
We did make some final improvements to our project before considering it finished. We implemented a method to only send data when a roll is done, as previously it would send that dice side repeatedly. We recreated our dice to a minimal size while incorporating our battery into design. Due to the hard nature of our dice, we created an elastic environment for rolling consisting of a t-shirt pulled lightly to allow bouncing. The roll detecting did cause a slight delay in the delivery of our data, as we have it set to only send the data once the same side is detected n times.
This is a basic overlay of the components and architecture. On the right, we have a clear flowchart that shows the flow of data from part to part and basically just how the whole system works. On the left, we have our components. So our seed, it has the IMU sensor, the gyroscope, and Bluetooth connectivity. The ESP32 has Wi-Fi connectivity, acts as our central processing unit, and also has Bluetooth connectivity. InfluxDB is our time series database. We used it to read and write data from and to the database. This was done using LAN protocol via HTTP POST or GET, and we also utilized the REST API. Hello everybody, my name is Jordan. I'm with Digital Dice and Database, and here is our dice. You can see the board right there. It's embedded inside this 3D printed dice. It has a slot on top for charging that we left, and we've since super glued the lid on so that way it doesn't come off when you're rolling it. It's a C-JAL BLE Sense. It has an IMU, which is an accelerometer basically. It many times has a gyroscope attached, and it allows us to read the dice side value and then transmit that via Bluetooth to our ESP32, which is actually our central processing unit in this project. So let's hop to the code. This is the device ID that we'll be advertising, and then we add the accelerometer data as a characteristic to that device ID, and we do setup. We have some exceptions. We set the local name for the device as IMU sensor. So that's what you would see if you were using Light Blue or another app. And then we add the characteristic for the accelerometer to the device ID basically. When we begin advertising these. So it'll print this while it's waiting for connections. But once it does find something and something connects to it, it'll let you know what it's connecting to. And then it will go through this loop, and it will stay going in this as long as it's connected. So it'll read the X, Y, and Z accelerometer values, concatenate them into one string Excel data, and then it will write that value to that characteristic that's going to be read by the other device. And then it'll also keep printing it so you know what's being printed. So just to give you an idea, you can see that as you move the dice or turn it, the values change. This is what allows us to basically determine the dice side on the ESP32 is using this data. So this is our ESP32 code. We have the Wi-Fi, we have our InfluxDB connection, and then we have the same dice device ID and the characteristic that we're looking for. We have some flags that help with the project, and then some more values that also help with the project. I'll explain in a little bit. So we begin by setup. It connects to the Wi-Fi and then begins scanning via Bluetooth for a specific ID, which is what's advertised by the dice. If it finds a device with that, it sees if the name is IMU sensor. If it is, then it basically kind of skips through this and goes down here and verifies it also has the accelerometer data characteristic and begins to basically read that. So then that goes down here, read accelerometer data characteristic, and we used a buffer to split apart the X, Y, and Z again, and we keep track of what values were as they're being sent. The reason we did that is because we wanted to be able to roll it land, and only send it once, instead of repeatedly sending the same side over and over and over and over and over again. This will actually only send it once, which allows us to do statistics on it. And then this is one of those flags, if dice is stable and significant movement detected. So that's just kind of how we do this. It creates a line protocol data, which is what InfluxDB uses, and that's created here. You have a variable, a tag, and the field key, which is the actual data you're sending, which is the dice side in our case. And then it sends that data to InfluxDB using our function. And that is using HTTP post. And it lets you know that it sent it. And this is where we determine the dice side. So we have a threshold. Basically, if it's greater, less than, you'll know which side it is on according to the rotation of the device. So let's go to InfluxDB so you can kind of see this in action. So here, 2 is the last one. So we'll put it on 5 and give it just a second. And then run it. And, oh wait. Here we go, 5. Yes, that's right. So instead of doing statistics on here, we actually did everything a little bit different. We didn't use Telegraph or Grafana. We actually have our data pull back from InfluxDB using a Python script that writes our data to a CSV for permanent storage, just so that way if we wanted to do statistics on 1,000 rolls or 10,000 or 100,000, it may not be feasible for us to just sit here and roll the dice all day. That way we can always keep track of current data. So it writes to data.csv, and it uses the time from InfluxDB and the value of the dice from InfluxDB, and that writes that to here. So we currently have 199, and if I run this, you'll see that it starts writing. Everything in the past hour, I believe, is what it's set to, or 15 minutes. So I'll end that. And then the way we actually do data analytics, or analytics in general on our data, is we have another function or another script that reads from the CSV, uses the timestamp and the value basically, and then plots it along with counters for each value. So we actually thought that 4 would be the greatest value, and that would be because the board's here, and due to the weight of it, we thought that it would majorly land on 4 facing up, which is the side that registers. But we either didn't do enough tests, or our assumption was incorrect, or it could also be just because of the rough sides of the edges make it hard for it to roll super freely. But 4 was actually not the leading. 4 actually came in 4th place. First was 2, then 3, 6, then 4, then 5, and then 1. If you have any questions, feel free to reach out, and thank you.
So for the challenges we faced, the greatest challenges we faced was the connection between boards initially. It seemed the seed shell BLE sense can only handle a single connection at a time, while it can advertise many. This meant we were finding the seed, connecting to it, but then not getting any data. The second greatest challenge we faced was figuring out what method of testing we wanted to do on the dice, whether that was predicting dice side before it landed, the bias of it, among other options. We did have minimal trouble with the initial connection to InfluxDB, but it was less connection trouble and more not knowing how to use the database. The only other trouble we had was with viewing our data in InfluxDB. We decided to go with testing the bias of our dice due to its design.
Now about the bias expectations. We had expected our dice to have a clear bias towards the side with 4. This was due to the internal design having the board on the opposite side of 4, which would cause that side to be weighed down and the dice to land more on 4.
After 200 trials, it came out that our initial expectations for bias were not correct. Our expected bias of 4 came in 4th place, whereas the level of bias remains unclear. They seem rather balanced. The most size is 2 right now, which is actually on the print bed is the topmost die, so the way that it gets printed. That may be a cause of bias. We'll have to explore that a little further. But right now, with our InfluxDB data, it looks pretty all right. Final thoughts for the project. One of the first goals we did not finish was adding multiple dice and aggregate counts from multiple sources. It's trivial to add another Zhao board, hard coding it in the files of the ESP32. It's rather difficult to have dice dynamically drop in and out of the system, and that will require a little more work, as that was the final week of work and we just couldn't get it up and running. We also want to purchase a smaller battery, as our current one has a little more power than we need to. I just wanted to be extra careful when ordering in case I'm not really sure how batteries work. So a smaller battery might be possible. We want to try and fill the dice completely with filament or resin or some sort of filler to give it a little more weight. Right now, it feels rather light to roll. We'd like to create a more sophisticated process for transmitting data and possibly have the computer do central processing as to prevent delays in transmission. The ESP32 has to calculate the dice size from the accelerometer data, so it takes up some time, and adding more dice to that system slows it down even further. It had been super cool to create a custom board containing only Bluetooth and the IMU for a smaller size. That'll allow us to have an internal battery already connected and a lot cleaner look, but that's a lot of complicated work, and a lot of us don't have that sort of embedded systems experience. Thank you so much for listening. Here are our emails. You have to reach out for questions. I'm super proud of the work our team accomplished, and I was lucky to have the opportunity to work with them.
Thank you.
Thank you.
Thank you. Thank you, everyone.